Howdy everyone, welcome back for Chapter 4 where we talk about reactions in aqueous solution. Chapter 3 was a lot about reactions that could happen with solids and gases, but this chapter is all about what happens when you have the reactants dissolved in water, what's going on, what makes them different, and how do they all interact with the water and with each other. So this topic covers a lot of different this chapter covers a lot of different topics. They connect in that everything's dissolved in water, but just be prepared that you might say, hey, this section seems a little bit completely different from the other sections. Yes, that's going to be true. But we'll get through it in chunks, but this would be a good chapter for practicing, this part goes here, this part goes here, and just, understanding how they go. Understand that you may want to pause at various points, say, okay, let me think about what we just talked about, and then move on. All right, so what is a solution? A solution is when you got a homogeneous mixture with two or more pure substances. And for this chapter, like we said, we're talking about aqueous solutions. So it's going to be most about water, where water is usually going to be our solvent. Officially, the solvent is whatever part of the mixture is in the greatest abundance, the most of it. But we do sometimes bend that definition where water is involved, where technically there are going to be some solutions where water may be in the minority, but we still say water is the solvent just out of convention. Everything else that's not in the greatest amount we call the solutes, and so when water is the solvent, it is an aqueous solution. All right, so here, since methanol is in much smaller amounts, water is the majority of it, this is an aqueous solution of methanol. All right, so an aqueous solution, when things dissolve in water, we talk about, well, what happens to that stuff? Well, a couple things can happen. If it's ionic, we say it dissolves by dissociation. They separate, the ions separate, and water surround all the different ions. So that's the picture down here, where here's a crystal of sodium chloride, where all the sodium and chloride ions are connected and surrounded by each other. But as they start to dissolve, you've got chloride ions that are surrounded by water molecules. You've got sodium ions that are surrounded by water molecules. And again, chloride, sodium, here's the sodium. Here you can see it kind of starting where the waters are pulling that chloride out. Waters are pulling that sodium out. And it would just continue until everything is completely surrounded by water. Then we'd say, okay, now it's done dissolving. There wouldn't be any solid left to see. Right? With molecular compounds, covalent and acids, they interact with water. Most don't dissociate. The acids do. That's what makes them acids. But if it's kind of what we call a pure molecular or pure covalent, then it's just going to interact with water, which is what we have here with that methanol again. The OH group of methanol will interact with the water there. They'll be surrounded by water. But the methanol itself, it's still the same molecule. The two parts of it don't fall apart there. And so all of it we're calling is dissolved by solvation, where you surround the molecule, whether it's a methanol molecule or these separate ions, they all get surrounded by the water. That's what solvation means. All right. We're not going to talk about electrolytes. We're going to ignore this table for a moment, mainly because it comes back about 10 slides later, and it will make a lot more sense then. But let's just focus on the definitions that are here. When we have an electrolyte, that is a substance that separates into ions when you dissolve it into water, and then a non-electrolyte doesn't. It does not separate into ions. So electrolyte, ions, non-electrolyte, not ions. And well, how do we know this happens? Well, we look at electricity, as you may have guessed. A strong electrolyte will dissociate completely when it's dissolved in water. So that's here like sodium chloride. It completely separates into sodium and chloride ions as it dissolves, and it conducts electricity very well. A non-electrolyte does not dissociate. It dissolves, but again, it doesn't separate. So here they add the sugar. It's a non-electrolyte, so doesn't conduct electricity, no ions. So the light bulb doesn't come up. And then in between it's a weak electrolyte, which we'll get to when we talk about acids. It only separates partially, so it will conduct electricity, but not as good. So sometimes you'll see a third picture that they don't have here of the light bulb, but it's only a little bit lit up. Notice pure water with nothing in it does not conduct. A common mistake that I see on some lab reports from a Chem 1 lab is that people say that ionic compounds will conduct electricity because there's metals in them, and metals conduct electricity. Yeah, metal, like solid metal wire, does conduct electricity, but that's not what we're talking about here. It's the ions are what are conducting electricity because they allow the charge to pass through. It's not that it's made from a metal, it's made from ions. That's the key part there, so make sure you don't get confused by that difference. All right. So what's the difference again between the strong and weak electrolytes? A strong electrolyte will completely dissociate, completely separate. And so when we do that, here's a strong acid that is a strong electrolyte. We use a regular reaction arrow to say, no, all that HCl aqueous, it really separates completely into H plus ions and Cl minus ions. So we use the regular arrow to show that it's a complete reaction. A weak electrolyte, on the other hand, only partially dissociates. Only some of it splits up. In fact, usually most of it stays together. So for that, we show it going back to Chem 2 with that equilibrium arrow, the double harpoon, to show that some of it separates, but some of it, or most of it, is still together. And so that double-headed harpoon, the equilibrium, that's showing no, everything is still present. It did not completely go. Some of it, because of that backwards pointing arrow, some of it stayed together. So that's only going to come up with acids. Ionic compounds are going to be strong electrolytes no matter what. Now, some of this is going to depend on, does it dissolve just in general? So not all ionic compounds dissolve in water. If they do, it's a strong electrolyte, but not everything dissolves. So we have to know our solubility rules. And we saw these in Chem 1, but they were usually provided on a little cheat sheet or reference sheet to look at. These will not be given on the AP test, so we need to know these rules. For the ionic compounds, ones that we need to know are the nitrate ion and the acetate ion. These compounds in this part of the table are the soluble ones, and there's no exception. So if you see nitrates or acetates as your anion, it's soluble. You don't even have to worry about what else is there. For three of our halogens, chloride, bromine, and iodide, these are usually going to be soluble. You just have to watch out for these three exceptions. Silver, this is called the mercurous ion, where it's the Hg2, 2+. And then the plummus ion, the Pb2+. The 4+, don't worry about the 4+. We'll try to limit it to these three. But if you get these three in there, well, then it will still be a solid. It will still be insoluble. So always watch out for those three. And then sulfate, another very common ion, it will usually dissolve, except with strontium, barium, again, the mercurous ion, and lead, 2+. So watch out for those four. So watch out for lead. You see, that's a very common one. Watch out for the mercury, but then know these other two. All right, so that's for the anions. The other solubility rule you should know that they left out of this table, I believe it's in the table in the book, but they left it out of this one. If you see for the cation, if you see lithium, sodium, potassium, or ammonium, and some books even include just all the alkali metals, group 1A on the far left, but if you see those, it's also going to be soluble. Just no matter what else it's paired with, if you see the alkali metals or ammonium, just assume soluble. All right, now this other half of the table that they put on the slide here are the ones that are usually insoluble. And I wish they had arranged these slightly differently, and I wasn't able to edit this table. The sulfide ion and the hydroxide should really go together, because if you notice, these are insoluble except with ammonium, like we said. The alkali metals, like we said, always soluble. Or these three, what they call the heavy alkaline earth metals, calcium, strontium, and barium. You see that it's the same exceptions for both, so that's why I wish they were together. But if you see any of those with them, then they will dissolve. Maybe not a lot, but they will dissolve a decent amount. For the carbonate and the phosphate ions, these are almost always insoluble, except again with ammonium and the alkali metals. So when you see NH4, think soluble. When you see lithium, sodium, potassium, maybe even rubidium, think soluble. those are, like I said, those are the ones that you should always just go with it. But again, watch out for calcium, strontium, barium. They're the exceptions here for sulfate, but then they're the exceptions the other way for sulfide and hydroxide. So there's less to remember as far as which ones. It's just you got to remember which way does it go. So take some time, practice these. Maybe make flashcards. All right. Well, once we have that information about what will dissolve and what doesn't dissolve, we can make some good predictions when we get what we call precipitation reactions. This is when you get two aqueous solutions where you had soluble salts in both, but then one of the products is going to be an insoluble salt. You're going to make a solid, and that solid gets called the precipitate. So these are kind of three synonyms you got to remember always go together. Precipitate, insoluble salt, solid, those are all the same thing. All right, so here's an example that I love this reaction, and we're just not allowed to do it in school because it involves lead. But you take some potassium iodide solution, which looks like water. You take some lead nitrate solution that looks like water. But when you mix them together, you start to see this bright yellow solid instantly. And what's happening right there is the lead iodide is starting to form. And it builds up in little particles here and there. That's where you get all the little powders. But then at the end, when everything mixes up, you'll get these nice layers of lead iodide. It'll still be in different pieces. It won't all make one giant piece. That would be a crystal. But you'll get lots of smaller chunks like this, and that's the solid lead iodide. And so we draw it together because it is together. It did not separate. It did not stay dissolved. So remember, if it's dissolved, it's all spread out, and we're just not showing the waters surrounding them all here. But when it's not dissolved, when it's insoluble, we draw it all together with no space in between. All right, so how are we going to predict whether we get a precipitate? Well, we need to look at our ions, and we need to look at our solubility rules. So we say, well, what's present in the reactants? So that's kind of saying, well, what if they didn't give us this product half? What if we just knew magnesium nitrate and sodium hydroxide? It says we should consider our possible combinations. So, well, we know how to switch that. So we'd say, well, magnesium could go with hydroxide. And then we look at our table to say, would that be soluble or insoluble? We'd say, okay, sodium's going to go with nitrate. And again, look at the table, would that be soluble? And so we'd say, okay, if magnesium's with hydroxide, well, that's the hydroxide rule. It says usually insoluble except with ammonium or a alkaline earth, or with the heavy alkaline earths, or an alkali metal. And magnesium was not there. Remember, it was calcium and below, and magnesium's above calcium. So that's still going to be a solid. The sodium nitrate still going to be aqueous. They're both very, very soluble there. So because we do have a solid, we have a precipitation reaction. We have a precipitate formed. Now that example where we switch the ions like that, that's called a metathesis reaction. In Chem 1 and Chem 2, we usually call it a double replacement or double displacement, and you can still call it that. Plenty of books do. But metathesis is maybe a new word that you haven't seen. It's for a Greek word that means to transpose or to exchange. And so the idea is you have exchanged, you have transposed the locations of the ions so that you get the new partners here on the product side. All right, so that's just what metathesis means. It's just a new word for something you've already been doing. All right, so how do we do that? Well, this is something that, again, Chem 1 or Chem 2 we've done. So we look at our chemical formulas to see which ions we have. We're going to figure out the products where we take a cation and pair it with a new anion, and we make sure we check our charges so we get the proper subscripts. That's the number one mistake. You can't just say, hey, it was a 1 on the reactant side, so it's a 1 on the product side. You need to go ahead and say, no, this is +2. That one's -3. When I switch it, okay, what am I going to get? Once we have that, we check our solubility rules to see should we write a solid or should we write a Q. Insoluble gets a solid, soluble gets aqueous. And then make sure before the end you balance it. So this is why we do balancing last. The charges, when we do that exchange to get the right formulas, things may not be lined up for conservation of mass. So we balance it at the end to make sure that it does. Steps 3 and 4 can be switched up depending on which one you want to do first. I usually do number 4 first, and then I go back. All right, so when we write these, there's a couple different ways we can write these, and it's not just for metathesis. We can do it for some other types of reactions as well. What we're used to writing, what we've been doing in Chem 1 and Chem 2, and even in this course so far, we've been writing molecular equations. But we also have these new ones that we call a complete or total ionic equation, and then the net ionic equation. And the thing for the AP test, when they say write an equation, they usually mean the net ionic. So that's what we want to default to, unless we're told just to write molecular. But AP likes to see net ionic, so we got to make sure we know how to get those. So the molecular, what we're used to, it just shows the reactants and products without indicating the ionic nature. It writes them as if they're molecules. So lead nitrate, it's PbNO3, and then two of them. Potassium chloride, KCl. Lead chloride, lead 2 chloride, PbCl2, and potassium nitrate. Everything's together. So it doesn't tell us anything about what ions are present. It just tells us, what if these were compounds, if these were still, solids, what would they be? But then we say, well, wait a minute, they're not all solids. We've got some of them are aqueous. What can we do about those to tell us more about the ions? And that's where we get the complete ionic equation. And so all the strong electrolytes, whether it's a strong acid, a strong base, or a soluble ionic, if it's a strong electrolyte, we're going to split it up into their individual ions. And so this is going to be a better picture, a better reflection of what is actually happening, what is actually in the water, what's actually separated. Excuse me. So if we look at this, well, the lead nitrate was aqueous. So that means we're going to have lead ions by themselves and nitrate ions by themselves. And then note the numbers. If we flip back to the molecular, it was Pb parentheses NO3 parentheses 2. And so that 2 applies to the nitrate. It does not go to the lead. So that's why we have one lead ion and 2 nitrates. And then notice the charges would work. +2 and then 2 minus 1s. Okay, yeah, that cancels out still. For the lead iodide, again, we'll flip back. So it was, well, they changed the chemical formula on me real quick. Pretend this was lead iodide, or pretend the other one's chloride. But there's 2 of them there. So there's 2 of them here. 2 and 2. In fact, I'm going to pause the video briefly to try to fix that. Alright, so welcome back. I promise I've tried to check these for typos before I start, but each individual slide there was correct, so I didn't notice they hadn't paired up correctly. So now we've made it lead nitrate plus potassium iodide goes to lead iodide and potassium nitrate. So here again, there were 2 Ki. There were 2 Ki's. So when we go ahead and split that up, 2 potassium and 2 iodides. Now the lead iodide is solid, so we keep that together, right? So if it's solid, it doesn't separate in the water, so it doesn't separate here. But the lead nitrate did. So again, 2 potassiums, 2 nitrates, because there was a 2 in front of the entire molecule, so that distributes. So this is the complete ionic equation, and so it shows you here are all these ions, or solids, that are present at both parts of the reaction, before the reaction and after. And that's useful, but as you notice, it's kind of taking up a lot of space. It kind of takes up some time to write this all out, and it's more information than we really need. So that's where we get the third type of reaction, the net ionic. The net ionic is where we're going to cross out anything that didn't change from the left side to the right. So from reactants to products, if something is the same, we get rid of it. So I'm going to flip back real quick. We say, hey, we got 2 nitrates over here that are aqueous, 2 aqueous nitrates over here. Same thing, get rid of it. We have 2 potassium, get rid of it. So if we go ahead and do that, we cross those out. The potassium, the nitrates, we call them spectator ions. They're just sitting there watching. They're floating around the water, not doing anything. So they're spectators. What's left over, that's the real reaction. This is what really happened in the water. So we had a lead 2+ ion react with 2 iodide ions, and they reacted and combined to form a solid lead iodide. That's the real reaction that happened there. With these spectators, they could have been other things as long as they still dissolved. The potassium could have been lithium, could have been sodium, could have been ammonium. Doesn't matter. The nitrate could have been a chlorate, could have been a acetate, could have been what. As long as it's soluble, that didn't matter. This part is what mattered. All right, so that's the net ionic. So you got to see what can be crossed out, and then what we really want, and this is what we'll be practicing a lot in this class, is what's left over, what really reacted. All right, so again, just summing that up, we're going to write the balanced equation for the whole thing like we normally have been in Chem 1 and Chem 2. We're going to rewrite it to split up the ions. And remember, only the strong electrolytes split up. We'll get to weak acids in a little bit. They would not split. But if it's a strong electrolyte, split it up and then cancel out the spectator ions and find out, well, what's left over. That leftover is the net ionic. All right, so now let's talk about those acids. Acids are substances that ionize to form H+. That's sort of the Arrhenius definition. But because H+ is just a proton, right? Hydrogen is proton plus an electron. If we remove the electron to make it +1, it's just the proton. Acids are often called proton donors. That's the Bronsted-Lowry definition of an acid. So here are some examples. We have simple ones like hydrochloric acid. We have nitric acid, sulfuric acid, acetic acid. So we have some that are binary, some that are ternary, some that this one's organic. And so when we're looking for acids, and I think this comes up on a later slide, usually the H is either written first or we get this COOH. That COOH means it's an organic acid. But either way, you say, okay, there's the H in the right spot, it's an acid. All right. Bases are substances that react with or accept H+, and they increase the concentration of hydroxide when you dissolve them in water. So the Arrhenius definition of a base was the hydroxide, but with accepting the H+, that's the Bronsted-Lowry definition. So using that one, it does not have to contain hydroxide to be a base. Here's an example of ammonia. This hydrogen from water can react and be transferred to the ammonia to give us hydroxide. So yep, it increased the hydroxide, because there it is, and it accepted the H+ over here, so now we have ammonium. And we'll talk more about these types of reactions. These are conjugate pairs. We'll talk about them more when we get to acids and bases later on in this course. But just remember, it doesn't have to be hydroxide to be a base. All right, well, how do we know? Is it a strong acid or a strong base? Well, for the strong acids, we need to memorize, but good news, we need to memorize 7 things. So HCl, HBr, HI, so 3 of our halogens, chloric and perchloric acids, so those go together, nitric acid, and then sulfuric acid, just the first proton. So H2SO4 is a strong acid, HSO4 minus is not. That one's a weak acid, so it's just the first one. But if you can memorize those 7, that's your strong acids. Now there are others, but they're much less commonly used. There's some really weird combinations of ions and other things to make them very strong acids. So they can be extremely strong, but because they're used so rarely and only in certain cases, we're going to call these the 7 most common strong acids. These are the 7 you need to know. For strong bases, these are the hydroxides that dissolve in water. So we have our alkali metal ones, so group 1A, lithium, sodium, potassium, rubidium, cesium. If you have those paired with it, yes, it counts. Or if it's the heavy 2As again, the ones that we said were soluble with hydroxide, calcium, strontium, and barium, those 3 are also considered strong bases because they dissolve and separate completely when they do. Right. If it's not on this list, it's weak. So here's just kind of a flow chart to walk you through it. If it's ionic and it's soluble, it's a strong electrolyte. If it's molecular, we got to check, is it acid or base? So here's our check for acid. If it's a strong acid, strong electrolyte. If it's not a strong acid, it's a weak acid, so it's a weak electrolyte. So that's an easy one to kind of remember. If it's a strong base, it's a strong electrolyte. Ammonia, since we mentioned it earlier, it's a weak base, so it's a weak electrolyte. So here, now this is that same table that was at the beginning of the electrolyte part. I'm not quite sure why they put it there as well. But here's the summary. So really, I think 1 through 4, it is correct with the if this, then that, and multiple ifs, it can be a little confusing. I think this table is a better way of getting the information down. So ionic, if they're soluble, notice here all these are soluble. If it's soluble, it's strong. None of them are weak. None of them are non. For molecular, the strong acids and bases are strong. Notice that they didn't put bases here because all the bases were ionic as well. But if it's a strong acid, it's strong. If it's a weak acid or weak base, it's weak. And everything else is a non-electrolyte. So there's your sugars and other gases and other things like that. All right, so talking about acids and bases a little bit more. The reaction between an acid and a base is called a neutralization reaction. If the base is a hydroxide, you will always get water and a salt, water and an ionic compound as your products. So here you go, the example that gets used more than any other, perhaps in all of chemistry, HCl plus NaOH, so hydrochloric plus sodium hydroxide, makes water and sodium chloride, so there's our salt. Now if we want to say, well, wait a minute, what's the real reaction here? We can write our complete ionic. Well, HCl is a strong acid, so it breaks up completely. Sodium hydroxide is a strong base, so it also breaks up completely. Water, as a pure liquid, does not break up. So kind of the rule for complete ionics and net ionics, a solid, liquid, or gas does not get split up. Aqueous gets split up if it's a strong electrolyte. All right, so water stays together. Sodium chloride is a strong electrolyte. It's soluble, so it splits up. And when we cross out the sodiums, when we cross out the chlorides, we get H plus OH minus goes to water. So that is our real reaction. And that's basically what almost every acid-base reaction goes to. It will simplify eventually to H plus to OH minus makes water. All right. Now, some of them don't quite give you what you might expect. And so these are the ones that have gas formation. And so when you have a carbonate or bicarbonate, a lot of times you'll still get the salt and you'll still get water, but you're also going to get carbon dioxide. And the reason for that, let me get my pen, is you can kind of think of it as having an intermediate product. It will form, let's use this top one here, it'll form CaCl2. But then if you switch the others, well, H goes with carbonate, you would get H2 and then CO3, right, to balance out the charges. And we call that carbonic acid, but this chemical is quite unstable. You can't keep it in a bottle. It breaks down quickly. It's an equilibrium reaction that favors breaking down. And this thing breaks down into the CO2 and the water. So you can see the H2CO3 goes to CO2 water. That part's balanced. And so we often skip even writing this part and just say, no, go ahead to the CO2 plus water because this is what you're really going to have the most of. All right. And same thing would happen here with the bicarbonate. You're just already one hydrogen on your way to the carbonic acid there. All right. There's another one here that it's the product you would think, oh, we have a sulfur here with H's here, so that's going to give us H2S. That is hydrogen sulfide. It does smell like rotten eggs, so you don't want to do this unless you're in the hood where it's going to suck those vapors away from your nose. But watch out for this one. And then there is a third one that sometimes comes up. They don't mention here, but I'll mention it briefly. If you ever form H2SO3 as a result of switching around your ions, so not SO4, SO3, this one also breaks down into water and sulfur dioxide, SO2. All right, and that one is a gas. All right, so these are the three kind of you have to remember for gas formation. The SO2, which comes from H2SO3. You have to watch out for H2S, and you have to watch out for the carbonic acid because it will go and make CO2 and water. So if you got those three, those are three to watch out for. All right. Now, how do we use these? Well, we use these hopefully not all the time. Hopefully your stomachs and esophaguses. We'll check on that one. Ask your human anatomy teacher. But this is hopefully you haven't been getting too much heartburn and indigestion at your ages. As you get older, no matter how much spicy food you're used to, it tends to get catch up to you eventually. But if you notice, they're all hydroxides or carbonates or bicarbonates. They're all bases. And so they're just going to react with the excess acid that's been formed in your stomach or esophagus and help neutralize it. And then, okay, now we don't have acid. So now hopefully the heartburn or acid reflux will go away. All right. Now this next section, it's a little bit different. I'm actually going to stop the video here for part 1 because it is so different and we're about at the half-hour mark. So we'll just pause there for a moment and then come on back for part 2.